Michael James Gratton. I am studying my PhD at the University of New South Wales. It's in symbolic reasoning, but this is another short paper, and I guess it's in part sort of a meta argument about the nature of cognitive systems, but it's also in part something of a position statement as well. So, any constructive criticism you might want to give me, it's more than gratefully welcome. All right, so getting into it. I guess the motivation here is cognitive robotics, which I guess, as you all know, aims to build robotic systems with cognitive capabilities that are approaching cognitive capabilities approaching what we can do as people. So learning, perceiving, taking action, predicting the future, that kind of thing. And so they're kind of cognitive robotic systems. They're kind of instances, real world instances of cognitive systems. There's now a number of these things around, and so it becomes an interesting question to be able to compare different cognitive systems and different cognitive robotic systems. And one way of doing that is by looking at the properties that the various systems have. This gives us a basis for comparing them. So, one system may have one particular property, and so it's in sort of one class, and a different system may have a different property. But it also gives us a way of better understanding specific systems, and it also gives us, the opportunity maybe to point out where some further research can be done. If we have, if we find a space where there aren't any current cognitive systems or cognitive robotic systems with a certain set of properties. And that's what this talk's kind of about. So what's the matter? I guess currently cognitive systems, cognitive robotic systems, kind of get classified into into these two broad families. One sort of is the cognitivist approach, which is, I guess, it's your classical kind of symbolic reasoning, knowledge representation based system, where an example of that would be, an example would be Shaky. A much later example would be some of the robotic systems we've seen at the conference this week. And that's on the one hand. On the other hand, you have emergent systems, which is kind of especially I think we as AI researchers, but also as codified by David Vernon, sort of group everything else that isn't a cognitive system into this sort of this group of emergent systems. And you have in there things like things that were developed, when there was some dissatisfaction arising with the cognitivist program. So Rodney Brooks started it all with his system, whose name just briefly eludes me. That's terrible. But also things like neural networks or dynamical systems. These are also examples of emergent systems. And so we have this sort of this broad distinction between these two, but I think there's a question of whether or not that actually well characterizes the differences between them. And I would argue that the distinction is basically a distinction of implementation detail rather than a distinction, a more interesting distinction that sort of teases out the differences between them. It's kind of like saying, comparing two programs and saying, well, this program is written in Haskell, whereas this program is written in C. It gives you some idea of some of the issues, what some of the issues that are required to go about doing this, to go about writing these programs, but doesn't really tell you much about what the programs themselves do. So, okay, an example of one of the properties, that sort of gets used to distinguish these two families is the nature of their mental representations. So on the one hand, cognitive systems have these abstract symbolic representations. If you had a robot that knew about your pet cat, then you'd have a cat symbol in its brain somewhere. Whereas emergent systems generally seem to have this sort of global system state. So you can't sort of noodle into its brain and say, okay, well, there's the cat, but rather you have to take its entire state as a whole. But I would argue that if you take, say, the knowledge base for a symbolic system, that really does constitute a form of global, of a global state. And so this particular property here, which sort of is supposed to differentiate between these two, doesn't really seem to do that very well. And another good example of that is this notion of embodiment, which we've been talking about at the conference a bit. Embodiment obviously is when you take a system and you put it in its environment so that it can not only be influenced by its environment, by perception, but also it can influence its environment back by taking action. And you have different different sort of levels of embodiment. Soft embodiment might involve simulation. Hard embodiment might involve actually building a robot and putting it in the real world. And this is kind of seen as a key property to differentiate these two families of systems, because it's necessary for emergent systems. Most emergent systems have their input strongly coupled with their output. So, for example, a neural net. In a sort of a connections kind of system, would its output layer is directly dependent on the input that it gets in. The result of the output layer is directly dependent on the input that it gets at the input layer, and so you don't really have there isn't really sort of an intermediate sort of stage there. There's a question of whether or not embodiment is necessary. Well, I think the general school of thought is that embodiment isn't actually necessary for cognitive style systems because as symbol systems they have this abstract representation that's decoupled from the world. So a cognitive system can just sort of go sit in the corner and cogitate and not really have to worry about what's going on everywhere else. But this is, I think this sort of, again, fails to sort of really distinguish between the two, because I think, if you look at some of the cognitive systems that we've seen at the conference so far, if you have a robot that does have a symbol system to do its reasoning, it's not going to really do anything if you take this robot out of its environment and just sort of have it sitting in the corner. It's not hard to argue for a cognitive system that does actually require some kind of embodiment to actually produce some intelligence. And so this is really kind of a question of, I think, embodiment is more of a question about whether or not a system has the ability to represent its world and deal with that, rather than whether or not it's actually in its world or not. And I'm running out of time really badly, so rather than relying on these sort of these ad hoc properties, taking a sort of a cue from philosophy of mind and cognitive science, I think that looking at the nature of representations is actually an interesting way of classifying these systems. And I don't know if I can go into the details because I am right out of time. But one property is the representational content. So what actually what a system's representations are made of. If they're systemic in the case of a symbol system, or maybe if they're like a sort of more of a global thing in the case of a connectionist system or a neural network or something like that. And another interesting property is it's the semantics of the representations. So does an external theorist have to come along and say, okay, well, this symbol here means cat, or can will the system develop its own sort of idea of what a cat is based on its capabilities as a cognitive system? And so if we classify some of these cognitive systems along these lines, you end up with a slightly better distinction. So rather than just having cognitive systems and everything else, you end up having, say, for example, physical systems are classified as a system with systematic representations, but with external semantics. And for example, a neural network might be sort of considered to be an unstructured, have unstructured representations, but with independent semantics. So like the neural net, through a process of, say, backpropagation, develops its own sort of representation of, of whatever it is that it's trying to sort of perceive or do. But importantly, like that highlights a whole. I mean, I don't think there's many, if any, systems at all that really that they use both systematics representations, but also have independent semantics. And I think that'd be that'd be actually quite a reasonable, quite an interesting research area. And that and this is following. Well, this is my proposal to sort of fill that hole. So basically, a symbol system that you can think of it as a symbol system that has as its domain mental objects rather than objects in the outside world. So rather than having rules that operate over, say, cats, you have rules that operate over representations, and then the job is to sort of, just summing up, I guess, the job then is to build such a system that can think using a sort of a theory of mind rather than a theory of, say, kitchens, if you wanted to build a domestic robot, or a theory of cats or something else. So you want to build a cognitive robotic system that can think for itself without you having to actually sit down and tell it what to think. Just quickly, I'm not affiliated with Alez at all, but I saw his talk at the Intelligent Robotic Systems workshop attached to AAAI this year, and there's some very interesting, there's a very interesting account of learning representational vocabularies for objects, visual vocabularies for objects, using a hierarchy of relations. And this approach I found quite exciting because it's sort of really sort of starting. It's the first system I've seen that's actually sort of taking like this approach that I was just espousing before. So I highly recommend you go Google them and maybe have a look at that work. But I think that's kind of it. I think I'm out of time. So thank you for listening to my very short talk. Come and see me talk at ICHCAI. I have a contextual symbolic logic paper in there, and that's kind of it. So if you have any questions. Yeah. Nope.
I learned that the eyeball is at the Sony.
Yeah.
Robot, right?
Yep.
They gave up the producing the eyeball robot.
Mm-hmm.
Because so many boys and girls complained that the eyeball did not give anything.
Yep.
The reason why that the eyeball robot did not give the emergent behaviors.
Yeah, exactly.
So the emergence is more better than the cognitivist. So do you think so?
Look, I think so. But I think this is why it's kind of interesting that if you take this sort of perspective on looking at the properties of a system's representations, you can see that there is sort of this space here, which is it's both. It sort of requires some kind of embodiment, whatever form that is, in simulation or something else, or at least sort of connected to some kind of input and some kind of output. But it retains some of the nice features of, say, using a symbol system, in that you can have, say, a functional story for your cognitive architecture, rather than relying on something like neural networks or dynamical systems. And yeah, look, as far as I've read, there aren't too many systems out there that sort of are sort of like that, like a sort of embodied symbol system, where rather than reasoning about some random theory, a theory of how to be a dog or something like that, or a theory of playing with children, you reason about your representations, and then the behavior arises from that.
Thank you. Yeah.